Thank you so much for having me. I miss not being in Hawaii, but hopefully I can steer some conversation. So today, I would like to talk about, what is the role of vision for robotic control? And is vision sufficient? Is vision the most important modality for control? Or are there other modalities which might perhaps even be more important than vision? So the talk is an exploration of, where we think we are today, which is a quest for making robots which are more general purpose, to moving towards robots which can be general and useful. And I think the big difference between robots being general, which means that they can perhaps perform multiple tasks, to performing them usefully, in my opinion, comes down to, what is their throughput, right? And throughput is something I define as how many times a robot succeeds, say in an hour, in a couple of hours, so on and so forth. And throughput, naturally captures these two things. One is how fast is the robot at performing the task. And if you look at, today's, robotic videos, especially the manipulation ones, most videos are sped up, maybe 2x, 5x, sometimes even 10x. So if we are speeding up our robot videos, it's hard to imagine how these robots are going to be useful in the real world. The second thing is, how do we make these systems be reliable? And I think this combination of speed and reliability is what would make robots which can do many tasks also robots which are going to be useful. So how do we move, from the left to the right? Uh, and I think the first thing which I think needs to happen for this shift is that we need to go from passive intelligence to interactive intelligence. Now, what do I mean by this? So, today's a lot of, robotic systems which are learning driven are inspired by the ideas which were originally developed to make large language models. And these large language models are really an instance of passive intelligence. What do I mean by this? Think about a sentence, I'm going to eat, where each word is denoted by a symbol S1 to ST. I'm using words, in essence, they're tokens, but, I'm just using the term words loosely over here. A large language model or a language model is something which would try to predict what is the next word going to be. For example, it could be apple, banana, or something else. Now, once the word is chosen, once I choose the word, AT, which ends up being banana, then, we are going to just go and append this word banana to complete the sentence, right? So, in a sense, the dynamics model over here is deterministic, right? So, given a sequence of words, there is a probabilistic model, which is a policy, which, has a distribution over words. But once we choose a word, then everything is deterministic. So this is how today's large language models work by doing next token prediction. And this is being done on a data set which has been downloaded from the internet. Now, if we compare this with the physical world, I think there are a couple of differences which become obvious. One is in the physical world, one never has access to the true state as one has access in language, but the sensing is noisy. Similarly, when you execute an action in the real world, that's also noisy. You don't have an exact action that you can execute. Finally, even the dynamics model is not deterministic, but stochastic. Right? So what this means is for the robot to be successful in the real world, it needs to learn the policy pi of theta on the data distribution, which is accounting for all of this noise. And this is what I call by denoisy, right? So this is where the policy has to perform good, accounting for all the noise which is going to happen in reality. So when we're doing, passive learning, what we're doing is we're relying on a pre-existing data set. Now, in such a scenario, the data set collector, for example, a human, if they're teleoperating robots or videos that we can find online, they have to capture the denoisy, but it's highly unlikely that a human who is who is mostly providing, positive examples, is going to capture all the noise that a robot is going to encounter. So, one hypothesis is that instead of relying on these passive data sets, if the robots can self-generate their data, then these robots are going to capture the right data distribution and therefore end up learning much more reliable policies. So to investigate this, we were looking at this very nice benchmark called Furniture Bench from Joseph Lim's group. And, in this benchmark, you have to arrange, a bunch of parts into a furniture. So we looked at this, very specific subtask, inserting the leg. And, what we were doing was we were comparing, these two approaches. One is doing behavior cloning from a fixed data set D, right? And, today, as you know, a lot of the behavior cloning approaches use this idea of action chunking, which means that they produce, a set of actions, and then these actions are executed one after another, but you don't really take the input while the action chunk is being executed. And what we found is, if you, do the behavior cloning approach, even though the number of demonstrations were increasing, we end up getting this performance saturation. And then, if we change the setup where we augment this behavior clone policy with a policy which is being trained with reinforcement learning that you're seeing on the bottom, this policy is collecting its own data, right? So it's correcting for the distribution shift which is happening. And this policy is also acting faster by taking in observations much more frequently. So the combination of these two things, to act, faster and to get data, from its own policy lead to, significant performance improvements, not just on this one task, but across different tasks as part of this benchmark, if you compare the blue and the red curves in the plot. So the point being that if we go from just passively collected data sets to interactively collected data sets, they can really help us improve the reliability of our robotic systems. The other thing, that we, also have been finding, and this is true of, most large models today, that they are static. What do I mean by this? By static, I mean that, if you get, Chat GPT, there's ChatGPT 3, then 3.5, then 4, then 4.1, then 5. You get these big releases. Now, after the model is released, these models are not learning after that, right? You can take some data, put them in context, do RAG, but fundamentally, you never change the weights of these models. Now, if you want a robotic system which we can deploy and forget, and this robotic system is truly intelligent, it needs to learn at its deployment time. It needs to account for the new scenarios which might happen at deployment time. So we do have to move beyond this notion of static models which never update their internal representations once they have been trained in a factory. And the problem that comes in with static or going from static to more continually learning models is that if models are learning continually in a lifelong fashion, they often encounter, catastrophic forgetting. So what we found in a recent work is that interactive learning forgets less. What do I mean by this? So what we did was we took a bunch of different tasks, and some of these are, LLM tasks, some of these are, simple, toy tasks. It's a combination, but this holds true even for, large models, a couple of billion, parameters. So what you're seeing on the x-axis is the performance of a task, a performance of a model as we are fine-tuning this model on a new task. On the y-axis, what you're seeing is the accuracy of models on the previous tasks. So blue lines, what they show is that the accuracy on previous tasks is good initially, but as you do more fine-tuning on the new task, the performance on previous task drops, right? Which is the classical catastrophic forgetting. So what we're comparing, the blue lines and the red orange lines are, when you take the same previous task distribution and the same, next task distribution, and depending on how you learn, whether you learn by doing supervised fine-tuning or SFT, which is an instance of passive learning, or if you end up doing interactive learning with reinforcement learning, there's a big difference in how much you forget on the previous tasks, right? So, we came up with this idea, which we call as the RL razor, which states that, among the many policies that reach a high success rate on the new task, reinforcement learning or interactive learning is biased towards scale minimal solutions, while supervised learning can converge to distant ones, which means that, RL is really finding solutions which are close to your current solution, and therefore it ends up achieving high performance on new tasks while not forgetting previous tasks. So this is, one more, point to, pointing out or suggesting that interactive learning might really be the way in how we make robots, learn when they are being deployed, right? And to, further this line of work, we had this another paper called Self-Adapting Language Models. And over here, the thesis is that as the robot is being deployed, it should not learn from all of its data. It should choose, what data it should learn from. So a good example is, students learning in classes. They get information coming from the lecture, they get information from the textbook, from the internet, maybe they go query chat GPT. But at the end of the day, many of us rely on making our notes, right? Where we try to decide what information to take from where. We resynthesize that information into a form which is much easier for us to learn from. This is how humans are learning. Versus when we think about, computer models or AI models, we just pass all the data into them, and then we hope that they're able to learn. But we think, that mechanism ends up being much more suboptimal. And this is what, we have been exploring, again, as a way to be able to learn more efficiently, at deployment time. And again, this is, again, empowered by interactive learning. Um, so great. So the next thing, I will consider is, what really is the role of vision as we're doing this interactive learning? Historically, one would, hear arguments that, visual cortex occupies more than half of the brain. So it must really be important for doing, sensory motor control. So how important is it actually? And I think it's useful to think about two distinct parts of doing control, or of a robotic system. One is planning and one is control. Now, what do I mean by planning is, suppose if I want to clean up my kitchen or put dishes in a dishwasher, deciding, which utensils go where, what is the sequence in which I'm going to keep these utensils is a planning problem. And I think vision is quite important in building plans. But when it comes down to, really picking up that plate, holding it, ensuring it doesn't slip out of my hand, and then inserting it in the dishwasher, that's when we are really commanding the robot to perform that task, which is a control problem. So if you look at, what's been happening in the state-of-the-art locomotion, for example, over here, a dominant paradigm has been that, hey, let's go to simulation, let's use reinforcement learning or interactive learning, collect large amounts of data. And, after that, we get these policies which work well in simulation, but we can then go and test these policies, in the real world, right? So for example, here's a robot, which is spinning, really fast. Here's another robot which we were deploying, outside a building. And what you find is at some point, a screw in the motor comes out. The robot keeps on limping, but it continues to perform this task. Another example is, this robot, dribbling a soccer ball on ice, everything running on board. But most importantly, all of the videos that you're seeing, all of this control is happening from proprioception, which means how much are the motors moving. There's hardly any vision involved except for tracking the location of the ball over here, right? Which is the plan of where I need to go. But how do I get there? How do I control my legs? That's all really happening based on proprioception. Similarly, if we are thinking about these robots which are becoming more athletic, Over here, we are throwing this ball far away, so the robot uses its entire body, or as you will see, you know, on the next screen, the robot is trying to pull this heavy set of weights. So all of this, problems of performing these tasks really do not require vision. They can be done, basically through proprioception. So in some ways, what all of these results in locomotion, not just these ones, but also coming from, other labs, is suggesting that proprioception by itself can take you quite far, right? Now we can, think about, what's happening once we go from four-legged robots to humanoids. Now, the same approach of going in simulation and training these robotic system works quite well, and this is what's been powering many videos that you see online today. But humanoids are much more complex in the sense that they are more unstable, there are more degrees of freedom. So typically, training humanoids is much more involved. It requires a lot more work in designing the reward function and setting up the environments. So what people have been doing is, relying on motion tracking. So over here, what you see is this purple humanoid or the purple target, which the black humanoid has to match. And, these humanoids are being trained to do motion imitation. And this is how, state-of-the-art humanoid systems today, for example, this video from Unit 3 is powered. So on the surface, this looks great that there is so much we can do if we were to track positions and let humanoids, follow these positions. But let's take a reality check. When we actually put these robots in the real world, uh, and I think one question you might ask yourself is, why are there all these humanoid videos where there are humans around humanoids just in isolation? And one of the big things is that, these humanoids are able to deal with the contacts that they're making with the world. For example, if the motion target is to spread your hands, as a human, if you hit an obstacle, you'll be fine. Nothing bad is going to happen. But for a humanoid, if it does that, it's struggles. Right? Here's another example where there's a motion reference to go, lift something and come up. It's lifting something which is probably a bit thin. But when you give something much thicker to lift, this humanoid, really becomes unstable. And the reason why these things are happening is because the humanoid has been trained really to follow the exact positions. It doesn't knows what to do when there's a contact which is being made with the environment. So in some ways, we are training these robots like stiff factory arms. We really want them to follow a sequence of positions. And this position following is a very, very vision-centric view of looking at robots. Now, in the real world, real world or the physical world is physical because of forces, F is equal to ma. And that's what we want these robots to be aware of. How do they apply forces in the real world and not just about how, in what position they should move. So what we did in this work, Soft Mimic, is to let robots learn how to apply forces and how to react to forces. So what you find is, these robots can be very compliant, so they can deviate quite a lot from their motion references, really, thinking in terms of forces instead of thinking in terms of positions, and taking the motion reference more as a reference instead of literally trying to copy it, right? And this is work done by Gabe and Michelle, in our lab. So here is, some illustrations of what happens when you have a reference motion, but you have something which is super stiff, versus something which is, much more force aware. It adapts to this, new scenario. Here's another example, where the robot is bending, but in the process of bending, if it encounters, a box, it will become unstable, versus a robot which is force aware, doesn't ends up, doing this. Here's one more illustration where the robot is pouring, some things through a bottle. And if you shake it, the robot, also suffers. Versus the robot is thinking in terms of forces, things are different. Even though we are disturbing one part of the body, the other part of the body, keeps on doing the same action. It's almost unaffected with what's happening on the other side. Similarly, we can take a single motion reference and, we can really give the robot these many different size boxes without requiring any training. And, this robot is able to comply and pick up these boxes of different sizes. And then this is again happening because it's thinking in terms of forces and not positions. It's not trying to match the position of a motion reference. It's not trying to necessarily detect where exactly the box is. It's trying to figure out, hey, where do I apply force? If I see force resistance, then it means that I have touched the object. I should just lift it up. Here is another example where we train the robot only to walk in free space, and then without doing any additional training, we can apply an additional load. For example, putting something heavy on a chair, and there was no training done or no domain randomization done to enable the robot to deal with this scenario, or when a human is interacting with a robot, right? The robot again complies very naturally because it's been trained to think in terms of forces or to act in terms of forces instead of positions. Right? So the one thing which I want to communicate is I do think a lot of current robotic systems are built with this idea of position intelligence, where the robot control is about going to a particular set of positions. And this is really rooted or deeply rooted in the idea that we want to do visual motor control, where we take vision as input and try to output positions. But I think to interact in the physical world, what we are learning from everything that we have seen in quadrupeds and humanoids and legged robots is that we should really be thinking in terms of, sensing forces and applying forces, because forces is the language of physical interactions. And it's really, really hard to see forces, right? So I do think this is not about vision. Forces is, different from vision. It's about touch, it's about tactile, it's about proprioception. And, we have seen, this rapid progress, happening in locomotion, but really not so much in manipulation, despite, so much research happening, which is all very exciting, but nowhere near the readiness which locomotion is at today. And my proposition is the main reason that's not happening is because we really don't have force intelligence built in to to these systems, right? Now, why would you care about force intelligence and manipulation? So here's an example. Suppose where we want a robot to go in and put in a screw in the slot shown on the top left. Now, if you're thinking in terms of positions, what you would do is you would try to get a screw, align it perfectly to where the screw goes in, and then try to move the hand down. Now, think about this, right? If you really want your neural network to predict, at a millimeter level, sub-millimeter level, this will require tons and tons of training data. We all know scaling laws in machine learning, which say that, to reduce the error linearly, you need exponentially more data. So this is going to be very expensive and hard to do. Versus if you look at, what a human is doing, the human is doing nothing which looks like position intelligence, right? It hits the boundary, it reacts to the boundary, the screw movement is quite clumsy, yet you're very reliable at performing the task, right? So force intelligence can help you get reliability without really being precise. And I do think, this is something very powerful. And it scales with how machine learning scales. You don't require exponential amounts of data to be able to perform these tasks as a human. So what if a robots could also, start doing this? So, why is this, harder to do this in manipulation than this is to do in locomotion? And really, it all boils down to the fact that a humanoid or a legged robot is running on Earth, and Earth doesn't move. It's really, really heavy compared to the weight or the inertia of the legged robot. But once it comes down to manipulation, things are quite different. The hand is typically much heavier as opposed to the object. So if the object, ends, if the hand makes a small mistake, the object is going to fly out, right? Just because the object is so much lighter than the hand. And this ends up really, really being the core problem, right? And to illustrate this, I like this visualization where imagine if you had to move a chair or if you had to move a strawberry and then you had a truck to move it. What's going to happen? It's going to be really hard to control it. And this is really what's happening, in manipulation today. We're using very, very heavy hands to control things which are very, very light, right? And the question which really comes down is, can we make these hands lighter? If we can, then things are going to be different. But then if you try to make hands lighter, you might say, hey, I can use motors which are lighter. But then light motors also have less power, and that really creates a problem. Um, so what do we do? So the one thing, that we have been exploring is, how do you make the system be light? One thing is, well, let me not have so many motors to begin with. So why don't we minimize the number of degrees of freedom, right? So we looked at, this study, which was done by, some people looking at hand prosthesis, and they were asking this question, how important are fingers and how important are wrists to, for hand prosthesis? And the TLDR and their conclusion is that two DOF wrists plus simple parallel jaw grippers are as good as 22 DOF hand. Now, I have, more slides showing this more quantitatively. If you're interested, I'd highly recommend reading this paper. But in interest of time, I'm going to jump ahead, taking the main takeaway, which is two DOF wrists and a simple gripper can be very, very powerful, right? But then if you go and look at the risks that we have in robotics today, they're not that good. So there's a UR arm, you can look at the Frank and many other arms. Even to make a small motion, these robots have to move so much. And this is because these wrists don't have joints which are co-located, but joints which come in a series. Right. Further, these wrists are also really, really stiff. Right. So what some students in the lab who are doing is they made this thing dexterous. So dexterous has joints located at a single location, which means that it can move, much more easily in clutter. And also, it's being built to, react to apply forces, and it can move quite fast. So as an example of the dexterous, uh, showing how dynamic the dexterous can be. This is a pre-programmed behavior. The other thing, you might have seen is that a lot of manipulation videos today are happening on these really uncluttered tabletop with a few objects which are there. Our households look very, very different from this, right? So, here is a comparison between what a default wrist and the dex wrist does. So default wrist on the left in orange, dex wrist on the right. So what you find is, because of this serial joint, the dexterous can go into these really small spaces and, bring out this, crushed piece of a drink versus if you don't have a, parallel wrist, you can't really go into these cluttered spaces. Here's again a comparison between, doing wiping and, by having this, force compliant wrist, you can do, things like wiping, much faster. You get some generalization for free as the person is, really moving this whiteboard while the wrist is wiping. Right? And what we also found is, if you do use the wrist, the length of your trajectories is, much shorter because you can move much more easily. So if you're collecting data, you can collect much more data. If you're doing learning, the advantage of shorter trajectories is it also increases your success rate because now you need to plan or you need to output fewer actions, which is always good for doing, machine learning. So the first thing, we can try to be minimal, in trying to reduce the inertia of the overall system. So, what I showed you is that wrist does this successfully. It's something which just improves machine learning for free. It also allows the robots to function in constrained environments. Now, but if you really want to do more delicate things, you still want to be fast, I think you want to be minimal, but not too minimal. And this is where we have been exploring how to construct robotic hands, which are there for being force aware, for really applying this philosophy of force intelligence. This is work done by Brandon and Hao Shu. This is our eyesight hand. This hand is quite fast. This hand is built for dealing with contacts with the world, while still retaining enough power so that it can lift regular day-to-day things. Some humans can go do pull-ups with two fingers. That's amazing, that's crazy, but we really don't need robots to do all of that. um, and these hands are covered in gel side sensors, so they are capable of doing fine grained tactile sensing. I'm going to skip this in interest of time. Next, what we did was, we took this eyesight hand and converted it into a device called, Dexop, which enables humans to control this, multi-fingered hand so that you can go and collect data, but really in a force-centric mechanism. Now, what do I mean by that is, right? So if you're doing teleoff, you almost never get force feedback to control the robot. Now over here, because there are linkages which are mechanically connecting the human fingers and the robot fingers, the human gets force feedback, at least the joint level, as it is interacting with the physical world. The hand is covered in tactile sensing, so we can record that data. We can also record the joint positions. Uh, and this is illustrating, this, Dexop in action, where, we are performing this assembly task. So over here, we are trying to assemble the hand itself. And what this is illustrating is the kind of things, one could do with Dexop while being able to record not just vision, but also being able to record all the force interactions which are happening as the hand is performing this assembly task, which also involves, at times manipulating, really small objects, as you would see, with this screw, and also using tools with a single hand because the other hand is already holding something, right? This is how learning with Dexop looks like. And we're calling this paradigm peri-operation, instead of teleoperation. Peri means something which is close, and our interpretation of this is that it's used, but because it is close and we can transmit forces, we can feel forces, and that's the benefit that comes by being close. So as a demonstration where we can record vision and tactile, and then we can go and learn a policy, which can, perform these, assembly tasks, as you see in this video. So the data that we're collecting is in a force-centric way, very, very amenable to, learning, policies. Now, these are some examples which are not autonomous, but just showcasing the design choices that we have made, which allow us to do, delicate manipulation, manipulate thin objects, be able to orient objects in hand, use tools with a single hand because many times the second hand or the third hand is occupied. And finally going and doing, very fine, steps of an assembly process. So here is the hand picking up an M2 screw, which is really the smallest screws that you can find. Uh, again, showcasing what you can do if you're getting, force feedback, both during data collection, but also hopefully when these policies are learned. Now, all of this was, to say that, hey, now that we have good hardware, on one hand, you can do, peri-operation to collect data in the real world. But then if we want to go and scale up the interactive learning paradigm, then we can take these hands and try to marry them with the power which comes from training and simulation. So while we haven't yet done that, but I'll just give a shout out to some of the previous work that we have done, showing how we can train, policies in simulation to reorient objects to the target location, for example, shown in the top right, and then go and deploy these policies, in the real world. Here's another example of the hand, reorienting this new object it has never seen before. And these demos by no means are perfect. The robot fails, half the time, but it's really showing uh, that these things are possible and can be, scaled up. And here's another example of peeling a vegetable, where all of this reorientation is essentially happening without vision. The hand can rotate these different vegetables, and when the second arm comes and peels it, you still have to resist all of these forces, to ensure the squash, never really, flies out, right? This was sort of work done by Tao Chen. I'm going to skip this in interest of time. The main TLDR is that reward optimization, reward design is a big problem. Today we use PPO, but if you really want to optimize rewards better, I do recommend looking at this paper called HEPO, which can work with much, easier reward functions. Again, I'm going to skip this, and really what I will end up with is this diagram that we want to robotic systems to achieve goals. For example, tying a knot over here. There are these two questions, planning and control. Planning, and these are not independent processes, right? I mean, they're tied with each other, right? Planning is to do with semantics, geometry, kinematics, motion description. This is the problem of vision, right? This is what's happening in digital intelligence, in LLMs, VLMs, VLAs, is to do planning. There's this problem of control, which has to do with inertia, dynamics, how is this motion actually realized, which I think is a problem of physical intelligence. And I do think, we need to move away from being position centric, but instead of having position only intelligence to force intelligence to actually make, reliable systems. With that, I'm going to, stop and, happy to take, any questions.